Okay, so in this lecture we will talk about the discrete valuation ring. Okay, the discrete valuation ring, right? So let me first define it, and then we will be proving each of the properties which are relevant to a discrete valuation ring, and then we'll set a very important example of it. Okay, so the definition goes as follows. Let K be a field. Okay, so we start with a field, then we define a function on it, and we call the function to be a discrete valuation. Okay, so a discrete valuation, on K is a function which we denote as V, which takes all the elements from the collection of all units of K. Now since K is a field, so the collection of all units are all the non-zero elements of K, right? So it maps it to Z. Since the image of this function is discrete, we know that the integers are discrete, right? Since the image of these functions are discrete, so what are we specifically doing is that, so if I just give a brief hint to the name of it, so we are sort of uh, trying to discrete out the units in K, right? So we are choosing the units in K and we are mapping it to a discrete set, right? So we are evaluating the units in K discretely. That's why the name suggests. So it's a discrete valuation ring. Okay, fine. Now let me choose. Okay, yeah. So discrete valuation ring on K is a function V from K cross to Z, such that, so it satisfies the following properties. Number one is that V is a map which distributes product to additions. Number two, V is a surjective map, and three, the addition is defined like this. So Vx plus y is greater than or equals to the minimum of Vx and Vy. Okay, and this happens for all xy in K cross with x plus y non-zero. Okay, now so this is the discrete valuation defined, right? Now we need to define the discrete valuation ring. So the set R, which is defined as the collection of all units of K, such that its valuation is, its discrete valuation is non-negative, including the element 0, is called the valuation ring, is called the valuation ring of V. Okay, so this is the definition of a valuation ring or a discrete valuation ring. Okay, or rather this is actually what we call a valuation ring. A discrete valuation ring is somewhat more specific, we will see. So observe that, or rather let me set it or we can do it one thing. So now claim that R is a subring of K. Okay, R is a subring of K containing the identity. Okay, so this is something which we need to prove, that R is a subring of K containing the identity. Okay, So let's prove this. Proof. So to show that R is a subring, we only need to show that R is a R forms an additive group inside K, or rather R is a subgroup, additive subgroup of K, and that R is closed under multiplication. That's all what we need to show, right? Okay. Before proving this, it's better, I guess, to prove something more important, or rather, yeah, okay, fine, let's do it. Okay, first let us prove this only. Okay, the proof. So let xy come from R. So what we need to show is that, so to show x minus y comes from R and xy comes from R. Okay, so to show that x minus y comes from R, what we in the background need to show is that if I choose an element from R, then its negative is also in R, or that its additive inverse is also in R. So to do that, first we prove a set of statements. Okay, so these are, so I'm keeping it for now. How do I select it out? Is there a way to select it? I guess there's a way. Yeah. So let me just select it for now. And have I selected it properly? Correct. So yeah. So let me just copy it down for now. Okay. I'll come to the proof a bit. Let us first prove some important properties of it. Okay. So some properties which can be sort of immediately evaluated. Okay. Right. What is the evaluation at 1? So I can write it as v times 1 times v of 1 times 1. By the property it's v of 1 plus v of 1. And so since these elements v, the images of each of these elements from F are in Z, Z is an additive group as we all know. So this implies that v of 1 must be 0. So this is first important property which we have. Okay. Now let A be in K cross. Then we know that A is a unit. So then we know that the image of 1 is 0, but I can write 1 as A inverse, but then I can write it as VA plus VA inverse. But this immediately says that the discrete valuation of the inverse image, the discrete evaluation of the inverse of an element is negative of the discrete evaluation of that element. Okay. So this is also a very important property. Fine. What more can we follow from here? Let me think of it. Okay, let's do it in this way. There is one more evaluation which we can try up. See, I can write 1 as minus 1 times minus 1, which I can write as v of minus 1 plus v of minus 1. But I know that the image of the discrete valuation of 1 is 0. So this implies that v of minus 1 is also 0, or rather 2 times v of minus 1 is 0, which implies v of minus 1 is 0. Okay. Okay, first thing first, I can write this assuming that the characteristic of K is not 2. Sorry. Wait. This evaluation is going on in Z, right? This evaluation is going on in Z. Okay, Z, the characteristic of Z is not 2. In fact, Z is not a field itself. So there is no question of talking it as a field. So Z is an integral domain, to be very precise. Z is an integral domain, right? So product of two elements is 0. So therefore one of them needs to be 0. Now 2 is non-zero, so v of minus 1 is 0. Correct. So I can write this as since Z is not, since Z is an integral domain. I got confused between the field being the domain and Z being the range. So Z is an integral domain. So this is the reason why v of minus 1 is coming out to be 0. Right? So this is the third important property, and the fourth important property, which I think I can evaluate it out, is that what is the discrete valuation of minus y. So this is v of minus 1 times y. but this is v of minus 1 plus v of y, but v of minus 1 came out to be 0, so this is v of y. So yeah, so let me just write it out specifically. So I have v of minus y is equals to v of y. So these are the 4 properties which we immediately came up using the properties of the discrete valuation. Okay. Now we will repeatedly use this. Okay. So now let me come to the proof of it. Okay. Yeah. So I had claimed this, right? So yeah, is the identity containing the identity. Okay. Now obviously it contains the identity, right? Why does it contain the identity? Because the image of the identity is 0. Right? The image of the identity is 0, and by the definition of the discrete valuation ring, it contains all those elements which are units in K, including 0, which are units in K or 0, and their discrete valuation is non-negative. So we just okay, since the discrete valuation of 1 is 0, this implies that 1 is clearly in R. So this is trivial, right? Okay, now let x and y be in R. Okay, now what is the valuation? So this means the valuation of y is greater than or equal to 0, since y is in R. So by definition it follows. But we just evaluated that the image of the image of the additive inverse of y is exactly equal to the image of the inverse of y, and this is also greater than or equal to 0. So that means minus y also is in R. So it's closed under additive inverses. Additive inverses dually exists, right? Fine. Now we can also show that so 0 is already included in it, right? We do not have to calculate anything about 0. 0 is already there inside the valuation ring. So now what is the valuation of x plus y? So we had given that the valuation of x plus y, this is greater than or equals to the minimum of vx and vy, right? But since vx and vy both are greater than or equal to 0, so their minimum must also be greater than or equal to 0. So this is greater than or equal to 0, right? So this means that x plus y is also in R, right? So what we have shown x plus y is in R, we have shown minus y is in R. Now what is the valuation of xy? So we know the valuation of xy is vx plus vy. Now this is greater than or equal to 0, this is greater than or equal to 0, both are integers, so this is also greater than or equal to 0. So this implies xy is also in R. So what we have showed 1 is in R, we have shown x plus y is in R, we have shown minus y is in R. The associativity properties that hold trivially from the operation from the upcoming field. So we are done, right? We are done. So therefore so therefore what we conclude is that R is a subring of K cross with identity. I think I have forgot to change the okay. So let me just make it dotted, and let me just make one more change. So I apply it to all the pages. Correct. Okay. Fine enough. So we have proved that the discrete valuation ring is in fact a ring, and it's in fact it's a subring of K cross rather, right? So our next claim, is that for all x coming from K, either x is in K cross or the inverse of x is in K cross. Now this somewhat follows trivially from the operations we defined. Suppose, sorry, for the properties we proved. Suppose x is not in k, x is sorry, not k cross. It should be r. Sorry. So I claim that either x is itself in R or its inverse is in R. Yeah. So suppose x is not in R, then this implies that the discrete valuation of x, this is less than 0. Right? This immediately follows from the definition of the discrete valuation ring. But then this implies that the image, the valuation of x inverse, which we have proved to be minus of Vx, this must be greater than 0, because this implies that minus Vx is greater than 0, and this implies x inverse must readily be in R. Okay, fine. Our final claim. Our final claim is that I forgot it. Okay. Oh yeah, I recall it. Okay. X is a unit in R, a unit in R to be precise. It may be a unit in K. I'm not concerned about that. It should be a unit in K rather if it's a non-zero element, because K is a field. So X is a unit in R if and only if its discrete valuation is 0. Okay. So this some sort of characterizes all the units inside the discrete valuation ring. The elements inside the discrete valuation ring will be units inside the ring if and only if its valuation is 0. Okay. Firstly, suppose x is a unit in R. Now this is the trivial part. Okay. Now since x is in R, this implies that this is greater than or equal to 0. Since x is a unit in R, from here I can have that the inverse of x is also greater than or equal to 0, because x is a unit in R means that the inverse of x exists inside R. So its inverse exists, so x inverse is inside R, and so its evaluation must also be greater than or equal to 0. Okay, but I know that this implies that minus Vx is less than is greater than or equal to 0, which means Vx is less than or equal to 0. So we have an integer which is both greater than or equal to 0 as well as less than or equal to 0. So both of these collectively conclude immediately that its valuation must be exactly equal to 0. Okay, fine. So now we need to prove the converse part. Okay, how do we prove this? See that, okay, so recall that, okay, so I am readily using it more over and over, so I'm just still writing it for completeness. So we have this, right? So I am assuming the converse part. So okay, let me write it afresh. I'm getting confused with myself. Okay, yeah. So assume, right, so assume that v of x is 0 to show that, now x is obviously by definition 0 because the discrete valuation is defined over the non-zero elements of the field. So I cannot define it for the 0 element. X is by definition non-zero. So to show that x inverse is in R, right, that is what we need to show. So this will imply that x is a unit in R. Okay. Now what is the evaluation of x inverse? We know that it's minus Vx, but Vx is 0, so it's 0. So it's non-negative, right? So it's non-negative. So this implies that x inverse, so v of x inverse is greater than or equal to 0 by definition, which implies x inverse is in R, right? So this was very easy, right? Okay, fine. X inverse also is in K cross. That's quite trivial, right? There's nothing complicated about this. Fine enough. Now what we are intended to do actually is talk about a very one of a very special case of this discrete valuation rings, which is the p discrete. It's called a p discrete valuation over rationals. Okay, so a specific case. Okay, so let p be a prime. Let p be a prime. and yeah, so P is a prime, and let K be Q from the definition of discrete valuation. So we are just dragging down the previous problem. So K equal to Q from the definition of discrete valuation. Okay, fine enough. Okay, define the map Vp from Q cross to Z such that Vp of a rational number, a non-zero rational number. So Q is a field, right? So A by B will surely be non-zero. So Vp of A by B is alpha, where A by B can be written as P to the power alpha times C by D, such that P does not divide C and P does not divide D. Okay. Now it's a very routine check that it's indeed a valid valuation, discrete valuation. So we are not going to get into the details. So you can just check that this is a discrete valuation. Okay, this is a very routine check. There's nothing too specific about it. What we need to check is the following. Okay, so claim the corresponding discrete valuation ring, or the valuation ring. Let me just, or rather let it be the discrete valuation. So the corresponding discrete valuation ring R consists of all rational numbers whose denominators are co-prime to P, are co-prime to P. Okay, so this is the first thing which we need to prove. Okay, so the proof, for simplicity, let me just set some notations. So let lambda be the, so this is the capital lambda, I guess. Yeah, so let this be the collection of all elements A by B, such that, or rather it's the collection of all elements A by B from Q cross, such that P and B are co-prime. Now we have a prime P, so P and B are co-prime. It immediately means that P does not divide B, right? You need to keep in mind that. So this is trivially playing the role that P does not divide B, okay, because we will be making use of this. Okay, so first let me prove that if I choose an element out of this set, then it will be in the discrete, in the valuation ring. Okay, so yeah, so for completeness, let me first recall how the R look like. So R look like all those elements, since we are talking about rational. So let it be X by Y coming from Q cross, such that their discrete valuation is greater than or equal to 0. Okay, fine. So now let A by B come from lambda. So I need to show that this is an element of R. To show that this is an element of R, I need to produce a rational number C over D, such that I can write A by B equal to P to the power alpha times C over D, such that alpha is greater than or equal to 0. Otherwise, because we need a valuation to be greater than or equal to 0, right? Now observe the important cases here. Suppose P does not divide A. Suppose P does not divide A. So there can be only two possibilities, right? Either P divides A or P does not divide A. Suppose P does not divide A. If P does not divide A, then I can write A over B as 1 times A over B, and I can write 1 as P to the power 0 times A over B. Now you can immediately observe that this representation actually corresponds to the definition of alpha as given in the definition of this discrete valuation, because P does not divide A here, since P does not divide A, and since I have chosen A by B from lambda, P and B are co-prime, so P does not divide B as well, right? Since this happens. So if this happens, this means that the discrete valuation of A by B is 0. So suppose, yeah, fine. So now let P divide A. Now if P divides A, that means the prime factorization of A contains the prime factor P, right? So now there can be some some alpha times P is existing as a factor of A. So I can drag out all the factors of P, and the rest of the elements will be eventually co-prime to P, right? So this implies there exists some alpha greater than or equal to 0, rather since P divides, so this is strictly greater than 0, such that I can write A as P to the power alpha times C, such that this the part C of the prime factorization of A, it contains no existence of P, right? We have dragged out all the elements which are concerned about P. So such that P cannot divide C anymore, because there are no P's left inside the factorization part of C. So this implies I can write A by P as P to the power alpha times C by B, and we can immediately see that P does not divide C by the way we have taken C, and P does not divide B by our assumption. So this implies that the discrete valuation of A by B is alpha, which by our construction is greater than 0. So therefore this implies that this element A by B, it is in R, or which implies that lambda is contained in R. Fine. So now we need to prove the other way conclusion. Okay. So conversely, okay. So let A by B be an element of R. Okay. So this means that the discrete valuation of A by B, which is some alpha, this is greater than or equal to 0, or which implies that there exists C by D in Q cross, such that, because A by B is non-zero, the representation in terms of C by D should also be non-zero. P to the power alpha can never be 0 because P is a prime, so C by D must be non-zero, such that A by B is equals to P to the power alpha times C by D, such that P does not divide C and P does not divide E either. Fine. So I need to show, so this is important to note down, I need to show that so what do I need to show? Yeah, I need to show that P and B are co-prime, or which is equivalently speaking that P does not divide B. So let me choose, or let me assume the contrary. Suppose P divides B. This implies that there exists some integer k such that B is equals to Pk. So therefore A by B, which is equals to A by P times K, this is P to the power alpha times C by D. So I can cross multiply by P, we are inside the rationals. So A by Pk, or rather I don't need this P anymore, right? Fine. So I have A by K is equals to P to the power alpha plus 1 times C by D. P does not divide C and D here as well, right? So we have achieved that V of the valuation of A over K is alpha plus 1. Fine. Okay. Now observe what happens. So this is something which we have observed. Okay, sorry. Yeah. So this is something which we have observed. Fine. Now the valuation of A by B, this can be written as the valuation of A by K into 1 by P. Now recall the definition of the valuation, it distributes multiplication into addition, right? So this is the discrete valuation of A by K plus K 1 by P, right, plus P inverse, right? Now So let me just reason it out here as we were doing. Now what is the valuation of P? Say I can write P as so P is same as P over 1, which I can write as uh, P times 1 over 1, right? Now P is a prime number, so it's obviously not 1, so P won't divide this, P won't divide this as well, right? Fine. So this implies that the valuation of P is just 1, but this implies that the valuation of the inverse of P, which we had proved in the previous case to be minus of Vp, so this is minus 1, right? Okay. So what do we attain from here? No, I am actually getting it to be exactly equal to this, right? It's not actually sufficing the proof, I guess, right? No, we can't go about in this way, I guess. No, this won't be a good way to do it. Okay. So I need to, at some point, I need to reach this contradiction that the discrete valuation comes out to be negative, which will contradict that A by B is coming out to be an element, right? But how can we actually read this contradiction? So till now the proof was quite simple, but I got evidently stuck here, right? Yeah. So let me go back and let me check what I did. So I have P dividing B. I have assumed P divides B, so I can write B as P times K. So I am getting A over K equals to P to the power alpha plus 1 C over T. Fine. Fine enough. So from where can I come up with a contradiction? Let me go back to the properties once. Okay. Okay, fine. If there is some position where I will eventually get a negation, I'm good to go, right? The only way to have a negative number is the inversion, right? Is the inversion. Okay, okay. Something which we immediately conclude as well is that the valuation of P is 1, or which implies that the valuation of its inverse is minus 1. This is something which we have already in hand. Okay, but what more can I do from here? Let me just check it once. Right. What should be the valuation of B? There is no P does not divide B. We have assumed P divides B, right? Right. So from here, can I conclude anything? Okay, this thing is something which I have reached honestly. What more can I say? Okay, this is the problem when I film something. I get stuck. Let me just think of it once. So yeah, fine. Yeah, I did it all right. Yeah, I did it all right. But where am I getting stuck? Okay, one way to proceed it might be like this. Okay, let me not be in this way. Let me not do it in this way. Okay, fine. Okay, let's do one thing. So I need to show that P does not divide B, right? That's something that's what I need to show, right? So suppose, okay, let's do one thing. I've got an idea. Suppose A is equals to P to the power m times C, such that, so I'm doing the same thing. Okay, I'm factorizing A in terms of P. Now obviously M can be 0 as well. Okay, I'm not restricting that P, that P will always divide A. Okay, so if P does not divide A, then A will be then M will be eventually 0. Okay, so I can do this such that P does not divide C. This can be done, right? And let B be P to the power n times D such that P does not divide D. Okay, I can do this. I can surely do this. But then by our assumption we have V of A by B, then it will become M minus N, and this needs to be greater than or equal to 0. Okay, clear? Okay, now the thing is that, okay, right, I need to make use of the fact that whenever I choose a rational number, I can consider it to be in its lowest terms, right? Yeah, I can do this. So now observe that now A by B is of this sort, right? The way we have constructed it, right? Now P does not divide P does not divide C, P does not divide D, C and D. So C does not divide B and D does not divide A, right? So the only only common factor between A and B, it resides in the powers of P. So I can assume without loss of generality that A by B is in its lowest terms, correct? I can do this, is in its lowest terms, but then M needs to be 0 or N needs to be 0. But if M is equals to 0, then the discrete valuation will come out to be less than 0. That's not possible, right? Which is not possible because we have considered the discrete valuation to be greater than or equal to 0, choosing A by B to be an element from the ring, so which is not possible, right? Therefore N needs to be 0, and once N is 0, we know that P does not divide B. Fine. So I actually don't need a contradiction here. Have I erased the statement? Yeah, I actually don't need a contradiction. I'll get a direct evaluation that P does not divide B. Fine. Okay. Or rather, which implies that PB is 1. Fine, this was the trick. Right. Fine. All's well that ends well. Okay, so the last claim I make is about the units in R. So claim, or rather, we find the units in R. We find the units in R. Now recall that X is a unit in R if and only if its evaluation is 0. Okay. So let A by B be a unit in R, then this implies that the evaluation of A by B needs to be 0, right? But what does it mean by the evaluation being exactly equal to 0? Okay, so now if the evaluation is exactly equal to 0, what can I immediately conclude from here? So this implies that A by B equals to P to the power alpha C by D implies that alpha is equals to 0, right? But in this okay, right, I think I'm getting to it. But in this definition, recall that here P does not divide C. Now since A by B is chosen to be from the discrete valuation ring, therefore P obviously does not divide D. But since alpha is equals to 0, that means this C by D must be exactly equal to A by B. So since alpha is equals to 0, this means the representation of A by B is P to the power 0 times A by B itself, and that's the only representation possible in terms of the discrete valuation. But this implies that P does not divide A, right? Therefore the units in R is the collection of all A by B coming from R such that P does not divide A. I'm not anymore writing the condition that P does not divide B, because that's already the way the R the elements of R look like. Fine. Okay, so this is a very important sort of a very computationally complex example of a ring. Okay. Yeah. So I got stuck a bit, but again, all's well that ends well. So meet you guys in the next lecture.